Hello, everyone. So I'm just glad to present my joint work on uniform propagation of chaos for dollar exchange economics model. This is a joint work with Roberto from Chile. Currently, I'm a postdoc at the UMass Amherst, and our work is being recently published on European Journal of Applied Math. So let's start. This is the outline of my talk. First, let me briefly introduce the model. So this is the economics model. It's about dollar exchange. So the setting is you have n agents, and suppose I call S I of t the amount of dollar agent I has at time t, and assume that the system is conservative, which means that no dollar is out of the system, no dollar is input into the system. So basically, the dynamics consists of following. You pick two random agents. The agent I is called giver and agent J is the receiver. We're going to pick agent I according to a specific rule. That is, you pick the agent I, the giver, proportional to the amount of wealth he or she has. And you pick the agent J uniform at random. Then basically, I give J a dollar, okay? So this is very simple. You pick agent 2 random agent ij, I give J a dollar as long as agent I has a dollar. You pick the giver at the rate which is proportional to the amount of wealth the agent has, which means the wealthy the agent is, the more likely it's going to pick to give. So the dynamics is favorable to plural agents. That's why we call pool bias exchange model. And the numerical simulation on the agent-based level suggests the equilibrium distribution when the number of agents becomes large and you play the game for a very long time, it's going to converge to a Poisson distribution. Okay, so we are interested in a large n and the large t limit. So to show the so-called propagation of chaos, we can write down the evolution of a single agent because all the agents they are identically distributed, although not independent. You can write down an SDE for the evolution of a single agent, and you can try to send formally n to infinity, and you're going to end up with a limit SD, which is the mean field equation, mean field SD. And you can write down the evolution of the law corresponding to the mean field SD, which is infinite system of ODEs. Notice that this is actually a linear ODE system. So, and the previous work with Special Motsch established a finite time propagation of chaos, meaning that if you fix the k particle marginal and you pass to n goes to infinity, then the k particle marginal becomes asymptotically independent. And you can study the resulting, the long-time behavior of the resulting linear system of equations of ODEs. And you can show that the Poisson equilibrium with their mu is the average amount of money per agent, which is conserved. So this is the Poisson distribution with mean mu. And you can show the convergence to its equilibrium through the weighted L2 in the weighted L2 sense, okay? And another approach is developed by Nicholas Lanchier, and basically instead of sending n goes to infinity, showing propagation of chaos, and starting t goes to infinity in the limit, then instead you look at you fix n and starting the large time limit of the dynamics. And it turns out if you fix n first and sending t goes to infinity, the heuristic is that each dollar, if you look at each dollar, this is the dynamics is such that each dollar is equally likely to be in each agent's pocket in the long run. So in the end, if you fix n and letting t goes to infinity, it's going to converge to a multinomial distribution. And then you pass into n goes to infinity by counting the fraction of agents with exactly k dollars is going to give you the Poisson distribution, okay? So the main work with my collaborator, Robert Cortez from Chile, is try to improve the finite time propagation of chaos result to uniform mean time, so, which means we're going to show this, the chaos propagates with, no matter how large the time is. Okay, now our strategy is this. Okay, let's first introduce some notations. We call W1, which is March's distance of order 1 between the two laws, which are supported on non-negative integers raised to power d, and we're going to control the Washington distribution between the k particle marginal of the n particle n agent system and the law of the solution, the tensorize the law of the solution to the mean field system. And we use triangle inequality twice. Basically, we first control the Washington distribution between the k particle marginal to the k particle marginal of the thermodynamic equilibrium. Basically, you fix n and sending t goes to infinity. So this is the k particle marginal of the binomial distribution. And then we control the Washington distance between the k particle marginal of the binomial distribution to the tensorized Poisson equilibrium, and then control the Washington distribution between the k particle marginal to its equilibrium. So this is our strategy. So we first control the uniform to prove the uniform propagation of chaos. We do like 3 propositions, each one corresponding to the control of each of the terms here. So this is our strategy. Is summarized in this figure. Is pretty innovative. So let's first start it with the equilibration of the n agent dynamics. So as we said before, if you fix n and look at the motion of dollars, the dynamics is very simple. So basically, each dollar is going to move equally likely each time. Each dollar is going to update its owner at rate normal at rate 1, and you can basically couple them. Again, coupling the dollar-wise dynamics. Okay, so you employ the same jump time and pick the same dollar and same agent, and if you use this distance, but this coupling won't give you a good result because the bound we have is going to depend grows on n. Okay, so but if you couple the agent-wise, basically you count a fraction of agents with I dollars, and you use this distance, and then in this sense, we're going to have a good control on the coupling distance. And in the end, we have the proposition 2.1, which controls if you start the pool bias exchange model with two initial configuration, their Washington distance is going to control. Has a bound which is independent of n. Okay, this is very important. And in particular, if we start at this is construction at the agent base level. If you fix n and t, you are going to have the bound, the law of the whole full process to its thermodynamic equilibrium, which is binomial distribution. It's bounded by a bound. It's independent of n. Of course, a coupling of the full vector gives the coupling of the marginals. So passing through marginal, you have this bound. Then you're going to control the k particle marginal of the binomial distribution of the multinomial distribution to tensorize the Poisson distribution. To show this, we're again using a coupling approach. So this is our bound. So this bound behaves like a square of n. So it's basically kind of law of large numbers. So you know that it's very common to use when n is large. You can use Poisson to approximate multinomial distribution in some range. Okay, we're going to skip due to the time limit. I'm going to skip this description of the coupling, but it's very enumerative. So I encourage you to look at the details in our paper. Okay, finally, we need the equilibration of the mean field ODE to the Poisson distribution. So this is the proposition 2.3 is purely on deterministic dynamics. So you can study the ODE without studying the underlying stochastic process at all. But still, you can by doing the previous 2 propositions, you can still using a triangle inequality to control them. But there's, as I said in a previous paper, the inequality 20 is based purely on analytical results. This is just the study of ODE system. And finally, to prove the uniform propagation of chaos, we just use the previous a finite time propagation of chaos and use the three triangle inequality we mentioned before. The key idea is going to pick the bound is going to depend on n and t, but you pick t wisely so that you have the bound in each of the region. So these are the reference. I know I'm a little bit rushed, but I'm encourage you to look at the paper for details. Thank you. Bye bye.